In Chapter 2 we addressed the question how the motor behavior can be described and adjusted to the required motor operation. For the moment, let us put the operating ranges and limitations in the background. We apply a fixed voltage to the motor and record speed and torque. The speed as a function of the load torque follows a straight line which is described by the equation. Delta n over delta m being the slope of the line, called speed-torque gradient. It can be found in line 14 of the motor data in the maxon catalog. Kn being the speed constant of the motor in line 13 of the motor data. The meaning of the speed-torque line can be explained as follows. Without torque to be generated at no load, the motor speed is highest. The more torque the motor has to produce, it is, the higher the required load, the slower the speed. If the torque becomes too high, the motor cannot rotate anymore. It stalls. Alternatively, an explanation can start at standstill. At zero speed, the motor can produce the highest torque. It will start to rotate. However, the higher the speed, the less torque it can produce due to the increasing induced voltage. At the highest speed, no torque can be withdrawn from the motor. An additional remark. The speed of stronger motors is less sensitive to torque variations. They have a flatter speed-torque line with a smaller speed-torque gradient. What happens if the applied motor voltage changes? From the equation we see that the speed-torque line is shifted in parallel. At higher voltages, the line moves up. At lower voltages, the line moves down. Adjusting the voltage is needed to run the motor at different load operating points. Operation at a fixed voltage, increasing the motor voltage for acceleration. These voltage adjustments are typically made by the speed controller. The speed-torque line shifts with voltage. Therefore, for motor specification, a fixed voltage has to be defined. This voltage is called nominal voltage and can be found in line 1 of the motor data. In the maxon catalog, there are 3 motor operation points given at this particular nominal voltage. However, keep in mind that the motor can be operated at any voltage. The nominal voltage serves just as a reference voltage at which the motor data are specified. The maximum available supply voltage limits the achievable load operating points. All operation points above the speed-torque line at this voltage cannot be reached. For instance, the extreme operation point at the end of the acceleration. At the highest speed there will be less torque available, and the acceleration will slow down a little bit. The operation point at the high speed may just be reached in this case, but there is certainly no speed reserve. Let us come back to the 3 special operating points at nominal voltage. We start with the no-load operating point. No load is a little bit misleading because the motor is slightly loaded. There is no external load, but the motor has to overcome friction and losses. The real no-load operating point is not at the extreme left, but slightly shifted along the speed-torque line. There are 2 parameters describing this real no-load operation point. The no-load speed, N0, and the no-load current, I0. The no-load speed value in the catalog is given at nominal voltage. The calculation at different voltages is simple. The no-load speed is essentially proportional to the applied motor voltage, the proportionality constant being the speed constant. The no-load current is proportional to the torque losses. It's a measure of the friction in bearings and brushes as well as of the iron losses, for example eddy current losses. These 2 no-load parameters, no-load current and speed, can be used to easily test the motor. It is without the need to connect the load. The second operation point on the speed-torque line at nominal voltage is the nominal operating point. It lies at the border of the continuous operating range and is characterized by 3 parameters. In line 6 there is the nominal current or maximum continuous current. This limit is the maximum current that the motor can thermally withstand. It is without overheating of the winding at standard conditions. The related torque in line 5 is the nominal torque, in the meaning of the maximum continuous torque. The nominal torque is given as an output torque. It is related to the input current by the torque constant corrected by the amount of friction consumed in the motor. Friction here expressed as no-load current. The last parameter in line 4 is the nominal speed. It has no particular meaning. It's just the speed where the speed-torque line crosses the border of the continuous operating range. The last special motor operating point lies at the right end of the speed-torque line, where speed is 0. There are two meanings of this point. It can be a stalling or a starting point. 0 speed can occur because the required torque is too high. The motor stalls. Stall torque and the corresponding stall current can be found in lines 7 and 8. The second interpretation is that of a starting point. At 0 speed, the highest current and torques are possible. Hence, stall torque and current may also be interpreted as starting current and starting torque. Again, torque and current are related by the torque constant. The stall or starting operation point has some practical implications. What you can learn is DC motors have a high starting torque. This gives a high dynamic response. Starting and stopping of DC motors need high currents. Often, start-stop operation is associated with current peaks. Power supply and controller might have limited current capabilities that can restrict start-stop operation. This is particularly the case on larger and stronger motors with flat-speed torque lines and correspondingly high starting currents. You can calculate the starting current from motor voltage and motor resistance. The key messages about motor behavior are: motor operation is linear. It follows the speed-torque line, which is characterized by the speed-torque gradient. The line shifts in parallel upon voltage changes. No-load speed is proportional to the applied voltage, with the speed constant Kn as the proportionality constant. That's it. The chapter about motor behavior. You can find chapters 1 and 3 in separate video tutorials. They explain motor operating ranges and the properties of the winding series.